Good morning, students. I am Y.S. Chandrasekharaya, Associate Professor of Physics, Government Science College, Tumkur. So today in this session, I will going to discuss the rigidity modulus by dynamic method. So in the last session, we have discussed the rigidity modulus by static torsion method. That means to say, we can determine the rigidity modulus of the given material by different methods. So in this session I will going to discuss the determination of rigidity modulus by dynamic method. So the learning objectives of this method to understand the concept of determination of rigidity modulus by dynamic method. So in order to derive the expression for the rigidity modulus by dynamic method, we have to consider this diagram. So the operators used as shown in the figure. So in this the value of this experimental wire, the value of the rigidity modulus of the given experimental wire can be determined using this method. So the one end of the wire is fixed at its upper end at the torsion head. It is represented as H, and the lower end of the wire is fixed to the center of the bar exactly so that the bar remains horizontal. So in this method, the time period of oscillation or the vibration of the suspended body is observed directly. Its total mass kept the same throughout the experiment, and yet its distribution is homogeneously altered about the axis of suspension so as to bring a known change in its moment of inertia about the axis and also a change in its time period. So, in order to conduct this experiment, two slotted weights C and D of equal mass, it is represented by small letter m, are placed on the bar on either side at equal distance. So, that distance is represented as small d from the midpoint of the bar. This is how you are supposed to conduct the experiment. The wire is the wire is twisted through an angle and released. The system executes torsional oscillations about the wire as an axis. So then the period of oscillation T1 is determined. So it is given by the equation T1 is equal to 2 pi into square root of I1 divided by C. So I1 is the moment of inertia of the whole system about the axis of rotation, and C is the couple per unit twist of the suspension wire. If I is the moment of inertia of the rod about the axis of rotation and I is the moment of inertia of each slotted weight about the parallel axis through its center of gravity, so then according to the parallel axis theorem, we can write the moment of inertia of the oscillating system I1 as I0 plus 2I plus 2m into d1 square. So squaring equation 1 on both sides after substituting the value of I0 in the above expression. So then T1 becomes, when you square it, T1 becomes T1 square will be equal to 4 pi square divided by C into I0 plus 2I plus 2m into D1 square. So the positions of the slotted weights are now shifted to the new distance D from the midpoint of the bar, and the time period T is once again determined. So since the total mass suspended from the wire remains the same, there is no change in the couple per unit twist C of the wire. So then the couple per unit twist is given by the expression pi n r to the power of 4 divided by 2l, where r be the radius and capital L be the length of the experimental wire. So thus for the second trial, the time period is represented as T2. So then, similarly, we can write T2 expression as T2 square will be equal to 4 pi square divided by C into I0 plus 2I plus 2m into D1 square. So then, if you add these two, if you divide equation 2 by 1, that is T2 square divided by T1 square, so after that you will get the expression for the rigidity modulus as, after dividing, you will get 16 pi ml d2 square minus d1 square divided by r to the power of 4 into t2 square minus t1 square. So thus the value of n can be obtained. As before, r must be measured accurately in view of this its fourth power being involved in the expression for n. So I hope that students have all understood this better. So thank you.